Hello, we are here today in our section 4-2. We're going to talk about graphing rational functions. Now, we talked about graphing the inverse function, and our inverse function, if you'll recall, had those asymptotes at y equals 0 and x equals 0. Looked like this. And then you had shifts in your reciprocal function based on where h and k were, just like you do in a regular function. So right now we're going to go way back to topic 3, and we're going to try to remember how to do synthetic division. So we're going to rewrite this using synthetic division. So top divided by bottom. That means that we're going to have 4 as our leading coefficient, and we have 0 because we added, this is like plus 0 over here. And then in our box is our 3. And remember, we bring the 4 down, and then 4 times 3 is 12. This is our remainder, and we're going to put it over our, we're going to put it over our original function. So when we step this down, it's not 4x, it's just the constant 4 plus 12 over x minus 3. Or I can rewrite this into 12 over x minus 3 plus 4. So now this is our shift up for our horizontal asymptote up here at 4. And that 3 is still our shift over to 3 for our vertical asymptote. Then we need to see where we know that it's still going to have this shape to it because it looks very much like this. The thing to note is that this 12 on top, whether it's a 12 or a 1, that constant doesn't really matter because at some point the bottom is going to grow faster than the top. So a rational number is the ratio between two integers. A rational expression is the ratio between two polynomials. So where you have an expression on top and an expression on the bottom, a polynomial on top. The important thing is that your bottom can never equal 0. So your domain is going to change. And then a rational function is any function defined by a rational expression such that r of x is blah, 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 blah. So rational functions have that fraction bar. So now let's look at how we find our asymptotes for a rational function. So I'm going to write out the steps here. Your first step is to factor the top and the bottom of the function. So our top on this one doesn't factor, but our bottom does. So when we have 12, we get 1 and 12, 2 and 6, 3 and 4. 3 and 4 add up to 7. So we get x plus 3, x plus 4. For a vertical asymptote, the next thing is to find the vertical asymptote. So to find the vertical asymptote, this is where your denominator is equal to 0. And the reason we have an asymptote there is because the denominator can never equal 0 because we cannot divide by 0. So just a little reminder, you cannot divide by 0. So we set our bottom equal to 0, x plus 3 times x plus 4 equals 0. And you should remember that we're going to set each factor equal to 0. And so those are our vertical asymptotes. So x equals -3 and x equals -4 are our vertical asymptotes. Now, with horizontal asymptotes, there are 3 rules. So these are the rules for horizontal asymptotes. The first rule is that the degree of the numerator, so whatever the degree of your numerator is less than the degree of the denominator. So in this case, and I'm going to zoom this in, our degree here is 1 and our degree here is 2. So we have a polynomial of degree 1 over top of the polynomial of the degree 2. That means that our horizontal asymptote is always y equals 0. Always. Y equals 0. The next thing we're going to look at is if the degree of the numerator is equal to the degree of the denominator. So here, both of these are 2's. They're the same. If that's the case, then your y equals the ratio of the leading coefficients. So in this case, y equals 4/5. That is our horizontal asymptote. And then finally, if the degree of the top is greater than the degree of the bottom, then there is no horizontal asymptote. So let's go back to our steps. You factor the top and the bottom, you find your vertical asymptote, then you find your horizontal asymptote by comparing the degrees of the top and the bottom. And then using these rules, you need to take note of this. So in our original equation here, we have x to the first over x squared. So I say this one's bottom heavy, quote unquote bottom heavy, because the degree on the bottom is bigger. And so if it's bottom heavy, our asymptote is y equals 0. Now for example 3, we're going to go through our steps. So this is already factored. So our vertical asymptote is where the bottom equals 0. So it's going to give us x equals 4/3. So it's a little bit bigger than 1. Then our horizontal asymptote, when we compare 2x plus 1 over 3x minus 4, these are the same. So our horizontal asymptote is at that ratio. So y equals 2/3. So it's going to be a little less than 1. Now, to graph it, I'm going to go back to 2 and we're going to add the final step. Check a point in the domain on either side of the vertical asymptotes to see where the graph is. So when we do that, we know that -2 is in the domain, so I'm going to plug it in. We get 2 times -2 plus 1 over 3 times -2 plus 1. So I get -4 plus 1 is -3. -6 plus 1 is -7. So positive 3/7, which is a little bit smaller than 2/3. So we're going to be down here at 2, -3/7, and that means that I'm there. Then when I plug in 4, I get 2 times 4 plus 1, 3 times 4 plus 1, 9 over 12, which is 3/4, which is above it. So we're going to look like that. So there is how we graph our function. All right. Now, that being said, we're going to go on to example 5 in the next